And so, hi everyone, my name is Dinghuai, and today I'm going to talk about some works that's like in the joint space between generative models and some control perspective. So I think we are behind time, so I will be trying to skip some background. So I think currently there are like two main paradigms of doing machine learning. So the most commonly used is like people just learn from data. So it's like you have like a large corpus data, like probably like scroll from the web, like text or images, and you train like a probably very large generative models by fitting the data. So it's like through some kind of like maximum likelihood training or just some regression, and this like usually called the pre-training stage in the training of generative models. And another paradigms of machine learning is that it's more about how to make sure that your models follow a specific pattern or like pursue a desired property. So what does this mean? So imagine we already have a, oh, okay, I can just use the cursor. So imagine we already have a like decent generative models, and it can generate some like data like text or images. And after that, like we have external probably like black box or white box reward function or a critique function that can be used to say tell like how good or how bad the generated content is. So for example, in the visual generation space, it could be like a static score function that tells how good looking is the generated picture, or it could be like an alignment score, which is used to quantify like how alignments between the generated picture and the given text prompts. So, so therefore, sometimes this is also called alignments or like generative design. So in the next slide, I would like to relate this problem to probabilistic sampling. So imagine we have a, so this is a very simple example of a Markov decision process of how we can design this action and this sequential kind of actions that's eventually build up some complicated objects such as like molecular data or other general data. So in this example, our goal here is like basically doing probabilistic inference or probabilistic sampling. So by this, I mean that assume that we have a target distribution on this space of all like complete data. So like so each complete data has a corresponding density value. So this one has a higher density value, and we probably want to generate this thing with higher probability. And so basically, this is our goal. And on the other hand, we can think about we use a decision-making approach or a control approach to address this problem. So by that, I'm trying to say that we can learn a policy or like an agent with like forward policy, which I call PF here, which can navigate through this, say, Markov decision process and through some learned policy network. So this learned policy can be used to guide these agents to generate some data through a series of sequential decision making. So basically, this is a very high-level idea of what a generative flow network or GFlowNet is called. So basically, if we have a decently learned policy network, and we can think about if we have a higher probability of choosing a direction, then we can use more number of particles on the direction, more number of particles on that particular path to denote this higher unnormalized probability, and we would have this illustration of a learned policy network that can induce a flow network in this space of Markov decision making. Okay, so this is not only limited to discrete kind of data. So in continuous space, like continuous probabilistic sampling. So let's imagine we have a two-dimensional. So in this very simple example, I will just put a two-dimensional case here. So let's imagine we have like a very like a target distribution pi, which is like mixture of Gaussian shown here. And we probably want to use some kind of sequential distribution making idea to generate this, say, not very easy target distribution. So similarly, we can design an action space. So here we have a series of like different latent variables, and hopefully we want to learn a policy or like an agent that could say, transform the distribution a little bit and a little bit like at each time step. And basically using this kind of diffusion-like structure, you can gradually change like the simple initial distribution to a complicated target distribution. So this is actually reflected in some classical stochastic control literature in the sense that this is analogous in the sense that like we can model a stochastic differential equation, like we can learn the drift parts of an SDE such that we want to achieve some kind of like optimization objective. So for example, like there are some mathematical way that can turn this like goal of doing probabilistic sampling into like a classical like control objective. But I will skip the math here. So so next, like our goal is about like how we could like learn hierarchical like generative models. That's so basically what we want to model is like a conditional transition probability or like a forward policy, and it can be used to induce like a joint distribution in this trajectory space, like from x0, x1 to x capital N. So this is basically by simply define like a initial distribution multiplied by a series of transition probabilities. So our goal is basically we want to use some way to learn the policy such that the marginal at terminal time step can be used to approximate our target distribution pi. So how we can achieve this? So we have some like straightforward idea. So for example, imagine we can also do something that's very similar in the opposite direction. So like in the backward direction, we can also define like something like a backward policy, and which can also be used to induce probability distribution in the joint trajectory space by this kind of like a composition of many transition probabilities. And think about like if we can minimize some kind of divergence between this forward and backward joint distribution, and let's say like if this divergence can be minimized to 0, which means that the two distributions are like basically the same, then we can basically prove that the marginal distribution at the terminal time step of this thing will be like identical to this target distribution pi. So basically, given this information from this target density, we will be able to use we will be able to have some kind of like tractable algorithm that we can learn a policy that's induced this that can be able to generate the samples from this target distribution. Okay. So basically, in the last slides, I'm saying like some kind of like high-level idea of an algorithm that can doing an optimization in this like very high-dimensional trajectory space. So we know that these typically tend to be resulting hard optimization problem because it's like high-dimensional property. So in order to improve it, we have some like insight that we can probably first decompose it into like lower dimensional optimization problems, and then update them with like partial trajectories. So how would we want to do this? So imagine, So here is like a small piece from our generated trajectory, and like pi is our target distribution. And here we have like a short piece that from x transition to x prime. So we don't know the marginal density of this like yellow density function. So we just use the quotation mark, question mark here. So these two density functions, like they are, of course, they are not the same, like they are different. But we realize that they can be equalized by some like, a detail balance kind of like transition like equations. So it's not actually detail balance, but yeah, so we use a quotation mark here. And we also know that this yellow stuff here is like something we don't know, so we can use like a neural network to parameterize this unnormalized density function. So basically, we can like result in such an equation that every term is tractable. Like it's either we know or we have a way to model it. So we can basically design some kind of algorithms to train our neural network. So we have two neural networks here, like y is theta and y is phi. And we can train our neural network such that this equation can be satisfied. And a similar like tractable objective can also be derived if the partial trajectory is not only at the terminal time, but like in arbitrary places of the structure. So the resulting sampling algorithm would be something like similar to RL spirits. So first we use like our current policy to do a rollout to get some trajectory, and then we just break it up in some stochastic way to get some shorter pieces, and then basically we use a model. We use a flow function model to model like the marginal density of each time step, and then we like construct like a learning objective based on some generalized balance condition, and trying to make sure that like our model can basically backpropagate the information of the target density into each level of our model. So, so basically this will be our training algorithms. And like basically in our experiments, we'll show that under some scenario, it will be have some advantage compared to say previous like MCMC methods. So here the y-axis is like some kind of like it's an estimation bias of some computational statistic task, and the x-axis is like a set of different like empirical benchmarks. So basically, in this picture, we are trying to show that our method achieves like a lower estimation bias, which means better performance than previous like computational methods or even normalizing flow or other diffusion-based learning baselines. So okay, so in the next slide, next chapter, I will basically showing how a similar idea will be used to align like more like larger scale of generative models. So basically, since the popularity of stable diffusion, the application of text-to-image generation has been like more and more popular, especially in both open source and closed source communities. So basically, the paradigm is that we have a diffusion process in the latent space. So here we have a series of like latent, noisy latents, and our generation is basically conditioned on some text information. So we, like human, give some text instructions, and we use some kind of like text embedding models to draw text embedding and use that as a conditioning on each generation step of the latent diffusion model. And we can perform like a generative diffusion process in the latent space. And after that, we have like encoder and the decoder, when we can use the decoder to basically decode the generated latents to like a natural image space. So this looks good. And imagine we have some kind of like external reward information. So basically, we can have some like reward functions that's say text input of image and also like the text prompts to calculate some kind of like for example alignment score as like a reward information, and we want to design some kind of algorithms that can use this external reward information to basically align the generation of the diffusion models. So how are we going to do this? So in this particular diffusion alignment task, so imagine we have a diffusion process here. So from this page, I will use the notation from the diffusion literature where where the clean image is x0 and like the previous image like xt plus 1 or xt is like a noisy image. So basically, a generation will start from some noisy space and goes to clean x0, and at the end we will have like a reward function that's given to this x0 image. So this is particular like parallel to like our previously mentioned like sequential decision-making model, in the sense that we could build some kind of like learning criteria or learning algorithmic objective in the sense that we can use like GPRONet idea to perform diffusion alignments. So more specifically, so imagine in diffusion models, we have like a forward or like a denoising policy, and also like a noising policy that I use the notation of Q here. And we can basically learn some like flow functions here to help propagate the information from one time step to another time step. And of course, we also want to incorporate our like reward information from the last step of the generation into like our flow functions. So a question showing here is that it's notoriously hard to estimate either a flow function here or basically general value function in deep reinforcement learning. So here we use some kind of like idea from the inherent diffusion structure to help this estimation. So imagine we don't know how good this intermediate latent is. Like we don't know the quality of this noisy latent xt. So one thing we can do is that because when we train diffusion model, we are learning with like a denoising objective. So basically, we will have a neural network called x0 hat that can give us a predicted like clean image. So here x0 hat will be like a predicted denoise image based on this noisy latent xt. And then we can use this predicted clean image to query the reward function. And this will give us like approximate estimates of this intermediate latent image. So we can combine these estimates and also a neural network to model like our flow function. So this would give us like a much better empirical performance. So in like our experiments, like in the left figure, the x-axis is like the number of training steps, and y-axis is like the observed achieved reward values, and we show that like some variants of our methods achieves better like faster rewards learning effects compared to like previous reinforcement learning baselines. And on the right-hand side, we show that like here is like the beginning of the training, and on the right-hand side is like the end of the training. So we show that as the training goes from left to right, our generated image becomes more and more aligned to these like given text prompts. So in our last, like most recent work, we also extend this idea to more to use more like gradient information from the reward function. So basically in all common reinforcement learning paradigms, people only use the information from a scalar reward function. So this is typically because like in usual deep reinforcement learning applications, such as like Mojuko or like robot control, people don't have higher order information from the environments. Like people usually just have like a scalar function as a feedback. So as a result, the learning paradigm would be something like you matching a scalar which contains like some policy probabilities to another scalar which contains some other policy probabilities and some reward values. But in our application here in this image space, we realize that it's actually we can have like much more information from this environment. So this is because like both our model and our rewards function is like parameterized by deep neural network and is differentiable, especially because the image is like it's in a continuous space, so it's differentiable. So we can do something very simple. We can just turn a scalar matching objective into a vector matching objective, and by simply taking a nabla on both sides of the equation. So in this way, we can say take a nabla of xt on both sides of the equation, and this becomes like a gradient matching, like we are matching a vector to another vector. So this is not only for the intermediate balance equation, but also valid for like the last step, like for the incorporates of reward information. So here we can use some reward information, gradient information into our learning algorithms. So we find that this is like brings a much more efficient, like an effective empirical algorithms in experiments. So like here, the first row is like images from pre-trained model, and the second row is like it's like from our method called nabla GFNets, and it's like you can say it's giving like much higher reward compared to a pre-trained model, and also it brings like good-looking pictures also compared to other like previous baselines, including like our previous paper mentioned in the previous slides. And we also show that like our methods can achieve a better rewards and diversity trade-off. So in this visualization, like the y-axis is like the generation diversity, and the x-axis is like the achieved reward values. So here we notice that like if we really exploit the rewards function, it can eventually we might be able to achieve some very high reward values, but on the same time, like the generation diversity will be very bad. So in this figure, like we're trying to show that our method achieves like a better Pareto frontier, basically a better trade-off between like generation diversity and generation reward values, based on these like gradients informed reinforcement learning methods. Yeah, and yeah, so that's the last slide of my presentation, and yeah, thank you for listening. Where's the next?
Thank you for the talk. I was wondering on the last slide, actually, I might have misunderstood something, but so you very nicely have this like higher Pareto frontier there, and I was wondering if you think you could in some way extend this to go further down. So could you further increase the reward and achieve a corresponding like
Yes.
slightly lower diversity, but at this higher frontier?
Yes. So eventually we might converge to some place at here, like this. So this is because like when we design our learning learning algorithms, so we have a reward function, and if you really want like a high reward, you can put something like a temperature on your reward function, as you can imagine. So this is like some kind of hyperparameter you can tune, but on the same time you don't want your generation to be. So if you look at the third row, so if you unfortunately go to some like spurious modes. It can really hack the reward, but in some really bad way. So you probably don't want that. So it's kind of like you have some way to balance these two things, like the reward and the actual visual effects, and you probably don't want to go to an extreme like in experiment. Yeah, so that's how we conduct experiments. Yeah. Yeah. Oh, okay.
Okay, so I think, so thanks for the great talk. And in your first work, you talk about the Gflow diffusion Gflow sampler, right? I feel like it's kind of similar to the previous work on denoising diffusion sampler and also PIS sort of work. Can you point out the difference between your work and the previous literature, in some sense?
Yeah, so so the path integral sampler is basically based on the connection here. So the path integral sampler is a previous work that's directly optimizing this control objective as a so basically you use this equation as a loss function of the deep learning like model. So it will relies on like the whole computational graph of each like x1, x2, x3, x4. So it will relies on the computational graph to exist during the whole optimization. And also it will, it's an algorithm that requires the gradients of the density function because it's part of the optimization objective. And so that's the difference. And also compared to previous, like there are some like denoising diffusion samplers. So that falls more to the category of this page that they are trying to optimize some objective on the trajectory space. So it's like they have some kind of like probably KL-based divergence on the joint trajectory space, and also probably one's like a forward and one's backward direction. And there are something, it will lead to some loss objective that you can minimize, but on the joint probability space. So our method is kind of like a follow-up work based on their work that we want to further improve this based on some like more like reinforcements or decision-making idea that we can break the optimization into like lower, like shorter partial pieces.
Thanks for the great talk. Can you go to the slide where you show there's a monkey on the skateboard?
Oh.
So, yeah, so if you're looking closely, very interesting thing is that when your reward gets higher, it becomes more like cartoonish.
Yes, so yeah, that's very
does
good.
Does that mean like the models have just watched way too many cartoons than they should be, or?
Yeah, so that's a great question. So I also observed that phenomenon. So I believe it's one phenomenon of reward hacking in the sense that so the reward function it looks too many cartoon pictures, and in some somehow people gives like higher, maybe people gives higher scores when they label the data, and this data like being used to train like a neural reward model. So this is some kind of like rewards hacking phenomenon that's kind of implicitly hurts the training. So that's also one of the reasons that why we want to strengthen like the diversity as a metric in the last work. So because like when you optimize the reward function, you always go to this issue of like over-optimize, or you got some adversarial examples. And so you probably want to say, for example, either use multiple reward function at the same time, or use some kind of like diversity measure to make sure that you don't fall into some kind of reward collapse scenario.
Yeah, I see. So in this, like in this particular case, you are more likely to see a monkey on a skateboard in cartoon than in real life. So I guess there's a bias in this case. Can you do like constraint only generating like a real life monkey on a real life, skateboard?
Yeah, I think we can basically add that into our reward information. So you will also be kind of like the conditioning of the generation process, and I believe that would be like a great idea to like still performing reinforcement learning, but with some higher, like more specific control information
I see.
in the reward design. Okay, I think we can go to the next.
Yeah, I think due to time constraint, let's move on to the next talk. Let's thank the speaker again.
Thank you. Thank you very much.